Alright, so we're getting to the end of PreCalc here, and I have to introduce you to matrix operations, but also what a matrix is used for in order to organize data, how we're going to solve these linear systems using matrices. We're going to skip over a few topics that sometimes we do include in the PreCalc curriculum, so if you see me crossing off some problems, that's why. We're running a little tight on time, that's all. No worries. Alright, so first we're going to talk about the dimensions of a matrix. And the dimensions of a matrix are always mentioned in rows and columns in that order. So the dimensions of a matrix are rows by columns. So for instance, this matrix right here has one row going across, and then columns are vertical. So his dimensions are, well, hello, I just said 1 by 2. We write it like that. This matrix is also a 1 by 2. And if you're trying to add or subtract two matrices together, they have to have the exact same dimensions. So our new matrix, our resultant matrix is what they call it, is the position parts of the matrix have to add together. So 6 and 3, better known as 9. And then -2 plus 1, better known as -1. So your resulting matrix is still a 1 by 2, and it's 9, -1. So same thing here, we have a different dimension matrix, but we have 2 rows by 3 columns. This one is also 2 rows by 3 columns, so since they have the same dimensions, we're allowed to subtract these two matrices together. Which means I'm going to have a whole bunch of subtraction problems I have to take care of. Let's start with 1, careful, minus -6 is 5. And then 2 minus -5 is 7. And then -4 minus 3 is -7. So there's the first row of the resulting matrix. Let's keep going down to the second row. -4 minus -2 would be a -2. -3 minus 6 is -9. And then 1 minus 4 is -3. So there's our resulting matrix. Then they get a little more exciting because that was obviously way too easy for PreCalc. So here we have a 1 row by, there's 3 columns here. It's a little hard to tell because of the algebra. So you have a 1 by 3 minus another 1 by 3, which means we're allowed to produce a resulting matrix where we subtract the terms. So the first part of the resulting matrix is 4zx minus 2y. Well, in algebra, those are not like terms, so that's exactly what we're going to write down. 4zx minus 2y. Leave it. The next part of the resulting matrix is -3x, but we're going to subtract y plus 5. So here you have to be careful, because if you think about that algebra statement, -3x minus y plus 5, you would have to subtract both the y and the 5. So this becomes a -3x minus y and then a minus 5. I should have spaced this out a little better, my bad. The last part of our resulting matrix is x minus 5z, careful, minus a -1. So combining those all together, you get x minus 5z minus -1 is a +1. So there's our resulting matrix. It's algebraic. Don't be surprised if those are the kind of questions I would ask you, because, anybody can add numbers together, but, let's make it a little more exciting and have algebraic components so I can really, truly see that you understand how the resulting matrix is formed. So in this question, we have 2 rows by 3 columns, and then over here we have 1 row by 4 columns. Well, these don't have the same dimensions, so we're not going to be able to add these together. So you can say like DNE does not exist. You can just write me a message, dimensions are not equal, so I can't add them, whatever. Alright, this next idea here, where you throw a 3 in front of a matrix, this is called a scalar multiple. And it basically means to distribute a 3 multiple to everybody. So everybody here gets multiplied by a 3. Dimensions don't matter when you're multiplying with scalar multiples, just the resulting matrix is going to have the same dimensions as the original. So everybody hit by a 3 gives you a -6, a 9, a -3, and a 3. So here we have a scalar multiple on this first matrix, and then they're going to try to have you subtract this other matrix. Now I can already tell by the format they don't have the same dimensions, so I'm not going to bother doing this question because it doesn't exist. Try to trick me with a multi-part. Alright, this is a little more fun. Here I'm trying to ask you to come up with a scalar multiple. Or, I'm sorry, I gave you a scalar multiple. I want to know what the original matrix was. So basically you're doing the scalar multiple in reverse. So matrix Y would be what happens before you multiplied everything by -3. So if you think about mathematical inverses, basically we're just going to divide everybody here by -3. That's going to give us our original matrix of Y. So Y is, let's see, -1, -4, 7, and 7. And if you don't believe me, go back and multiply that scalar multiple in, but it works. So here we have almost like an algebra statement. I have some original matrix plus a mystery matrix gives me this new matrix. So if I'm trying to figure out matrix B, he's going to have the same dimensions, because in order to add matrices together, they have to have the same dimensions. So 1 plus something gave me 5, well, that something was a 4. 0 plus something gave me -3, well, -3. And then 6 plus something gave me 7, that something's a 1. Those are the kind of questions they like to throw on SAT and ACT tests just to see if you understand what a matrix is doing and how it's organizing everything. Alright, so now we're going to multiply matrices together. You are able to do this on a calculator. We'll do a lot of work on a calculator for, especially for row reduction and for solving systems with matrices, but you should know how to multiply a pretty basic matrix by another pretty basic matrix. And one of the major things that we have to understand is, are we even allowed to multiply them together, or is it undefined? So for your first matrix, you have, his rows by his columns. We'll call R1 times RC. And then for your second matrix, the one that directly follows it, you have his rows, so we'll call it R2 and C2. The idea is the number of columns in the first matrix has to match the number of rows in the second matrix. If these match, that means it's okay for you to multiply the matrix together. Now furthermore, the resulting parts here, this R1 and C2, those are going to be the dimensions, I should write that, dimensions of the new matrix. So if you look at the original dimensions of your two matrices, first I have to check if I can even multiply them together, and then I have to know what are going to be the dimensions of my new matrix, and then I can kind of set it up. The actual act of multiplying, though, is pretty intense. So, oops, I don't know why I scribbled that out. You're going to always check the dimensions first. So we have 2 rows by 3 columns here, and then we have 3 rows by 1 column. And I check the inner dimensions, which says it's okay to multiply together. And then I check the outer dimensions, which tell me my new matrix is going to be a 2 by 1. So what I'm going to do is I'm going to draw a skeleton for a 2 by 1. I'm going to make it kind of large this first time because I want to kind of write this out for my notes of where these numbers are coming from. We have 2 rows by 1 column. So boom, boom, gigantic column. You'll see why in a second. Then what I'm going to do, if you have other colors, this is a great time to use them. I'm going to take the rows of my first matrix and the columns of my second matrix, and I'm going to circle them. So there's 2 rows here. I'm going to circle them. There's only 1 column here, so that's good. And this is what we're going to do. This is where it gets kind of crazy. Basically, you multiply each position like 1 by 1, 2 by 2, 3 by 3, and then you add those results together. So like right here, 0 times -4 is, I need like a 4th color here. I don't know. Okay, 0, let's just write that out that way. 0 times -4, and then plus 2 times 0, plus -4 times 5. We'll simplify that in a second. Alright, and then the second row times that column would be, let's see, 4 times -4, plus -4 times 0. You won't have to write all this out every time, I promise. And then 6 times 5, plus 6 times 5. So what does that mean for my problem? Well, I'm going to write a much smaller matrix this time. The stuff I wrote in blue, 0 times -4 is 0, 2 times 0 is 0, and then -4 times 5 is -20. So 0 plus 0 minus 20, that first entry into the new matrix is a -20. And then for the green part there, -4 times 4 is -16, this is plus 0, and this is plus 30. So if I add those together, I think I get a 14. So yeah, it takes a little bit of work And I know what you're thinking, if I could do this on my calculator, why is she making me do this by hand? So we're going to see a problem coming up where you are going to have to do this by hand because there's an algebraic component in one of the entries of your matrix. Alright, so first check that we actually can multiply these together. So we have a 2 row by 2 column, and then we have a 2 row by 2 column. So the inside dimensions here match, which means it's okay to multiply together. And then my outside dimensions are going to tell me that my new matrix is a 2 by 2. Alright, see if I can. I'm going to start with a really big matrix so I can write out my work, because remember, these are notes. Alright, the next thing I'm going to do is circle the rows of my first matrix with the columns of my second matrix. Alright. Matrices are set up in like entries, so this first blank here we would call 1, 1, and this one here is called 1, 2. It means the first row, first column, first row, second column. Well, if you think about what I circled here, this is first row of the first matrix and first column of the second matrix. This guy here is first row of the first matrix with the second column of the second matrix. So if you're ever lost, like, oh gosh, what am I supposed to be multiplying together? Just look at the entries. It's like 1, 1, 1, 2. This would be 2, 1. This would be 2, 2. So again, second row, first column, second row, second column. Alright, let's do this. I'm going to try to write a little less work. I'm still going to kind of have one step to simplify though. So 6 times negative 3 is negative 18, plus negative 5 times 1 is negative 5. We'll simplify that in a second. And then I'm just going to move on to the next position, which is 1, 2. So still the first row, but now the second column. So 6 times negative 6 is negative 36. Right here. And then 5 times negative 5 is positive 25. We'll simplify that in a second. Alright, here 1 times negative 3 is negative 3. 3 times 1 is 3. Simplification coming. Alright, second row, second column. 1 times negative 6 is negative 6. 3 times negative 5 is negative 15. This is a lot easier to teach when we're in person because, like, basically, I can't do this on the backwards on the camera, but you're going to be moving like that with your fingers, basically. So the more mental math you can do, the easier this will be on you in the long run, that's for sure. Alright, so your last step is to actually simplify. So negative 8 plus negative 5, this entry becomes a negative 23. This is a negative 11. This is a 0. And then this is a negative 21 right here. Can't read that, but it says negative 21. So if I didn't have lack of space here because of my camera, I would have rewritten this matrix as negative 23, negative 11, 0, negative 21. And that is my resulting 2 by 2. So this next question, I have 3 rows by 2 columns in the original, and then I have 1 row by 2 columns. So if I look at the inner dimensions, since they don't match, this is not okay, which means that this product of matrices would be undefined. You can say does not exist, but technically the labeling is it's undefined. Alright, so here, algebra, here we come. This is a 3 row by 2 column, and then a 2 row by 1 column. We can multiply these together because of the 2 by 2 in the middle, and my resulting matrix is going to be a 3 by 1. So, 3 rows, 1 column. Make it kind of large because we're going to have a lot of algebra here. Alright. I'm going to circle the rows of my first column, or matrix, hello. Dyslexia, it's a thing. Alright, and then column of the second matrix. Alright, let's do this. So we have negative a times 6b is positive 6ab plus 4 times ba is 4ab. We will simplify that in a second. Alright, keep going. Negative 2a times negative 6b is positive 12. Oh, sorry, a squared. So 12a squared b plus a squared times ba would be a to the third times b. Alright, last row, same column. Negative 5 times negative 6b is 30b. And then 1 times ba is plus ab. So these aren't like terms, these aren't like terms, but that first one here, 6ab plus 4ab, we would simplify that together and make that a 10ab. But, ugh, that's gross. So that's the kind of stuff we have to be able to do by hand, so that's why we can't just be so reliant on our calculator, right? Plus, we all know about that dreaded half of the ACT, or the SAT that's no calculator. I think we're going to be skipping this in class for the idea of what a determinant is, but if you have a 2x2 determinant, what you do is you take the left diagonal and you subtract the right diagonal. So what I mean by the left diagonal is this one right here. And you multiply that diagonal together. So you do negative 2 times 3, and then you throw down a negative symbol, or subtraction symbol, excuse me, and then you find your right diagonal, which is 2 times negative 5, and you subtract. So negative 6 minus negative 10 is plus 10. So the value for the determinant of this 2x2 is 4. The reason we're skipping this in our pre-calc class is because we're going to skip the idea of inverse matrices. So we don't really have a use for determinants. If it shows up on an SAT test, though, they're pretty easy to come up with, so that's the good news. I think that's probably going to be the end of our lesson because we're going to be skipping the inverses. So as far as homework goes, I think there's the next worksheet in your packet. Looks a lot like this one where you have to do addition, subtraction, scalars, multiplying, also multiplying with algebra. Check your gold sheet because we probably shortened the assignment a little bit. All right. Have fun with matrices.